All right, today we are taking a journey deep inside the atom, right to its very heart. We're going to explore the nucleus, that incredibly dense, positively charged core. But to really get a handle on it, we first have to understand just how small we're talking.
So let's start with this analogy, because it really puts things into perspective. Imagine an atom is blown up to the size of a classroom. In that entire space, the nucleus would be nothing more than a tiny pinhead floating in the middle. That means an atom is almost entirely empty space. The part with all the stuff, all the mass, takes up a ridiculously tiny fraction of the volume. We're talking about 1/1,000,000th of the space.
So here's our game plan. First, we'll dig into that weird paradox of the nucleus being both tiny and massive. Then we'll break down what it's actually made of. After that, we'll look at how scientists classify different types of nuclei. And we'll finish up by exploring their shape and just unbelievable density.
All right, first up, the tiny, massive nucleus. Let's really get to grips with this contradiction. How can something that's practically invisible in the grand scheme of the atom be where almost all of its mass is hiding?
This chart really lays it all out. You can see the crazy difference in volume, that pinhead versus the whole classroom. But look at the mass. Over 99.9% of the entire atom's mass is packed into that little pinhead. The electrons orbiting around it, they barely weigh a thing. So for all practical purposes, when we talk about the mass of an atom, we're really just talking about the mass of its nucleus.
Okay, on to our second section. Let's define what a nucleus actually is. This means getting to know its fundamental building blocks and the key numbers that physicists use to describe every single one.
First off, a very useful term you need to know is nucleon. It's basically just a catch-all name, a family name, if you will, for any particle that lives inside the nucleus. It's simple, but it's important.
And here are the two members of that nucleon family. You've got protons, which carry a positive charge, and neutrons, which, as their name suggests, are neutral. They have no charge at all. As you can see, their masses are almost identical. But here's a really interesting quirk. A proton is stable all by itself. A neutron, on the other hand, is unstable if it's floating around freely. It'll actually decay in about 15 minutes. But tuck it inside a nucleus, and suddenly it's perfectly stable.
Now for the two most important numbers when you're talking about nuclei. First is the atomic number, which we call Z. It's simply the number of protons. This number is everything. It's what defines an element. 6 protons, you're carbon. 79 protons, you're gold. Period. Then you have the mass number, or A, and that's just the total count of all the nucleons, so protons plus neutrons.
So how do physicists write all this down? They use a standard notation for what's called a nuclide, which is just a fancy term for a specific kind of nucleus. Let's take gold as our example. The bottom number, the 79, that's the atomic number, Z. The top number, 197, is the mass number, A. And from this, we can figure out everything. A simple subtraction, 197 minus 79, tells us that a gold nucleus has 118 neutrons.
Okay, for section 3, let's tackle a really interesting question. If the number of protons defines what an element is, what happens when you change the number of neutrons? This is where the whole idea of classifying nuclei comes into play.
And that brings us to the most famous classification of all, isotopes. You've probably heard this word before. Isotopes are just different versions of the same element. They have the exact same number of protons, which means they behave the same way chemically, and they sit in the very same spot on the periodic table. The only difference is the number of neutrons they have, which just means they have different masses.
Hydrogen is the perfect example to make this super clear. All three of these are hydrogen because they all have 1 proton. That's the rule. But protium, the most kind, has 0 neutrons. Deuterium, or heavy hydrogen, has 1. And tritium has 2. They're all hydrogen, just with different weights.
So this probably has you wondering something. If an element like hydrogen or chlorine can have different isotopes, each with a different mass, why does the periodic table only show one single atomic mass? And why does it always have those weird decimal places?
Well, the answer is that the number you see on the periodic table is a weighted average. It's based on how common each isotope is in nature. Take chlorine, for instance. Out in the world, about 75% of all chlorine is the isotope chlorine-35. The other 25% or so is chlorine-37. So you take their precise masses and you average them out according to those percentages. And voila, you get 35.47, which is exactly the number you'll find on the periodic table.
And to wrap this section up, here's a handy little table that summarizes these classifications. We've talked a lot about isotopes, same number of protons.
But there are also isobars, which have the same total mass number, and isotones, which have the same number of neutrons. It's a really neat way to keep the whole nuclear zoo organized.
All right, for our final section, let's zoom back out. Instead of focusing on the individual particles inside, let's start thinking about the nucleus as a single object and explore its physical properties, like its shape and its density.
So it turns out from experiments that nuclei are basically spherical, and we can actually estimate their size with a pretty simple formula. In this equation, R0 is just a constant, about 1.2 femtometers, which is an absurdly small number. The key thing here is that the radius depends on A, the mass number. This tells us that the volume of a nucleus is directly proportional to the number of nucleons inside it. It's like every proton and neutron takes up a fixed amount of space.
So, if every nucleon takes up the same amount of space, what does that mean for the density? It means the density should be constant, and boy is it ever. The density of nuclear matter is about 2.3 times 10 to the 17th kilograms per cubic meter. That number is so huge it's almost meaningless. To put it in perspective, water is 1,000 kilograms per cubic meter. A single teaspoon of matter packed this tightly would weigh billions of tons.
And that leads us to this really profound conclusion. The density of a nucleus is constant. It does not matter if it's a tiny little hydrogen nucleus or a massive uranium nucleus. They are all packed to the exact same mind-boggling density.